The first thing that you're probably thinking about is I want to be able to get a statistically significant result at the end of my study. So there's a few things, and by doing that it demonstrates that the result is reproducible. And usually, if I'm sure you've all come across statistics, that it's usually done by saying what's the probability of the fact there's no difference between the males and females, and that's what the p-value is. So here, if we were looking at a males statistically, I put here heavier than females, and we've got a p-value from measuring weights in males and females. We end up with a p-value of 0.007, so that says there's a 0.007 probability that they're actually the same weight as females. So that's often considered as a reason to reject the hypothesis and conclude that we've got reasonable evidence that males are significantly heavier than females. So that's what we're after. So the first thing to consider is how large a sample, and I'm mainly going to consider that in the session later this morning. And also you want to consider what to sample. It might sound simple. I mean, in this case we just sample males and we sample females, but we certainly wouldn't want to say sample lots of observations on just one female and one male. That wouldn't be very helpful. So sometimes it's not completely clear-cut what we're sampling, and you want to think about that. And the other thing that statistical significance is going to be affected by is how much variability there is in the data. And often you can reduce this by considering various design measures, and I'll have a think about some of those a bit later. Then you want to make sure that you think there's going to be a statistical method that's going to allow you to reach your desired conclusions. So although you don't need to go into sort of really thinking about exactly how you're going to analyse the data, you want to know that, yeah, if I measure these, I can do a t-test or something at the end of the study, and that's going to be satisfactory for reaching my conclusions. I think it's fairly obvious we do need multiple samples. It's no good just taking one male and one female, because possibly the female might be taller than the male, and we wouldn't want to conclude that that means all females are taller than males. So we need several examples to allow us to generalise and ensure that the result is reproducible. Yeah, I'm not going to say too much about how many, because I'm going to concentrate on this in the next session at 11:30. Basically, you want sort of a large enough sample that you've got a fairly good chance of achieving statistical significance. You can never be completely sure, but you want to have a good chance of it. If it's only sort of a small 20% chance you might achieve statistical significance, it's really not much point in doing the study. But you don't want too many. You don't want to waste your effort and get your result kind of too easily, and even if it's highly significant, you might not have needed to have had as many samples. You're likely to reach your conclusions, but you've gone to unnecessary effort, possibly wasted animals as well. But you don't want to risk not drawing the conclusions. If there is an effect there, you want to be able to see it. So we'll be looking at that in the next talk. So I said statistical significance is affected by how much variation there is in the data. In some studies there's ways to try and reduce the amount of noise in the data. Sometimes if you're applying an intervention, it might be a treatment for a disease or some kind of intervention, and taking measurements to see what happens, it's often a good idea to take a measurement before treatment and then control for that in the analysis, and that can reduce the amount of variability in the data. Just thinking about your experimental methods and the technology, thinking about what sort of causes variability if you've got different people doing the experiment or taking measurements, and whether you can sort of, they might be a bit variable in how they assess something. If they're looking at an image or counting cells, you might want to make sure they're as consistent as possible between them. Other elements, if you can think of any ways to improve the experimental practice. If you've got animals in cages, try and make sure their cages are not in two different environments. That can reduce variability. Another thing is, quite often there are nuisance factors. Having animals in different cages, then you're not really interested in the cage, but it's a nuisance factor that can cause variability, and it's sometimes possible to design that out by using something that we'll look at a bit later called a randomized block design. Another example might be if you've got animals of different ages, that's going to influence the result, and you want to make sure they're evenly distributed between your groups. In some cases, it's possible to allocate interventions within individuals. Often this isn't really practical, but sometimes it is. For example, if you could treat different sides of the body, perhaps there's a treatment for eyes, then you give it different interventions. Then by comparing within the individual so that the results are actually paired, that will reduce the variability in doing your comparisons. So that also increases the chance of statistical significance. Another thing, it's not always practical to do this, is if you're taking measurements, you could reduce the measurement error by taking several measurements on one unit and using the average. However, if there's significant cost or time issue in doing this, it's not always the best way to kind of use your resources. This will reduce the amount of variability. Another thing you can do is think about selection criteria. For example, if you're studying animals, sometimes perhaps there's animals that have got unusual traits who might skew your results. If they have an infection before they come into the study, very sort of under or overweight animals might not be typical. You might think about setting selection criteria to make sure you don't get any really atypical animals which are going to skew your results. It's difficult to justify excluding them after you've done the study. It's worth thinking about that, but then again, you don't want to take out too many because it won't be a typical sort of set of animals then. I said you could reduce variation or what you might call noise in the data by taking repeated observations, and I thought it might be helpful just to show an example of this. In this experiment that was reported, then the weight of crabs was measured sort of on one occasion, and this is the distribution of the weights of the crabs that was obtained, a histogram showing how many were each weight. But you could potentially sort of recatch the crabs and weigh them again, and this is what was done in this experiment. They were actually weighed on five different occasions. So these histograms are all on the same scale. In the first one, they're just measured on one occasion. The second one, they were measured on two occasions and the average was taken, and you can see that the distribution, the variability is a bit less. And then in the third one, there were 5 measurements taken on each of the same crabs, and the average was taken, and the distribution, the spread, is even less. So of course the crabs still do vary between each other, but what this shows is that there's an amount of kind of measurement error, and on different occasions crabs were sort of heavier or lighter than other occasions. So by taking several measurements, we've been able to take some of that out of the variability, and if we're doing a study of crabs and we went on to analyse, that would give us a better chance of statistical significance. However, as I said, it's not always the best use of time to take multiple measurements, but if it's quite easy, you're just taking, I don't know, sort of measurements, samples from a tissue, and it might be possible to take more and average them. So that's something to consider.